Hello, welcome to my talk, Generic Reed-Solomon Codes Achieve List Decoding Capacity. I'm Josh, and this is joint work with Sivakanth Gopi and Visu Makam. To start out, let me introduce error-correcting codes. A code is a subset of some space sigma to the n, where sigma is our alphabet. The rate of the code is the logarithm of the size of the code divided by n, and the distance of the code is the minimum Hamming distance, that is, the number of symbols in which the two code words differ between the two distinct code words. Now, in most applications, we work with linear codes. So a linear code is a k-dimensional subspace of some vector space fq to the n, where fq is a finite field of size q. The distance can then be thought of as the smallest Hamming weight of any non-zero code word in the code. Now, this code can have different representations. One such representation is with a generator matrix. A generator matrix is a k by n matrix where the rows of this matrix form a basis of the code. A dual perspective is instead a parity check matrix, where each row of the parity check matrix has the property that if you take the dot product of it with any element of the code, you get 0. Another way to think of this is that H is a generator matrix of the dual code. We shall use both of these in our talk today. Now, every code, linear or not, satisfies what's known as the singleton bound, that the distance of the code is at most n minus k plus 1. There are a class of codes which achieve this bound, which are known as maximum distance separable codes. For our purposes, we can think of a maximum distance separable code as one in which every k by k submatrix of the generator matrix has full rank, or has non-zero determinant. We'll come back to this later. Now, MDS codes have a number of applications. However, there are also many applications where something better than MDS codes are needed. And we're going to explore now a few of these generalizations. One application of MDS codes is in the construction of list-decodable codes. Here, a list-decodable code, you have a receive message y, and you want that there are only a few code words that are close to this message y in the Hamming distance. We say that our code is row, L list decodable if for any message y there are at most L code words that are close to y, as in a distance of row times n. A stronger notion is what is known as average radius list decoding, where for any L plus 1 code words, it's not just that one of them is excluded from this Hamming ball of radius row times n, but rather the average distance is greater than row times n. And it's easy to see that average radius list decoding is stronger. Now for any n, k code, one can prove a generalized list decoding singleton bound, which has appeared in a few places in the literature, which shows that this radius row is at most L divided by L plus 1 times 1 minus k over n, or 1 minus the rate r. As you send L to infinity, you just get 1 minus r, and this is known as the list decoding capacity. A recent work of Roth extensively studied codes whose average radius list decoding radius matches this list decoding singleton bound for a specific list size L, which we'll call LD-MDS-L. He showed that LD-MDS1 is equivalent to MDS. That is, optimal unique decoding of a code is equivalent to being MDS. Further, if you have LD-MDS of 1 over epsilon, as epsilon goes to 0, you're achieving list decoding capacity. Thus, it's quite important to figure out which codes satisfy this LD-MDS property. Another application of going beyond MDS codes is the study of maximally recoverable tensor codes. So in a tensor code, you have two codes, a column code and a row code, and you can think of the tensor of these two codes as a matrix, where every row of the matrix is in the row code and every column of the matrix is in the column code. Such codes have been used in real-world applications. MR means that they're maximally recoverable. That is, any erasure pattern, say if you think of each node as like a server, or any combination of the servers going down, that's information theoretically possible to recover from, your code is actually capable of recovering from that. So now we're going to look at a restricted case in which the column code is a parity check code. What properties of the row code are needed such that this tensor code is MR? Turns out this is also a generalization of MDS codes. Another question you might ask about MDS codes is constraints on the generator matrix. As previously mentioned, a generator matrix of an MDS code is a basis of the code. There are many different choices of the basis, and some of them have more zeros in them than others. So let's say a zero pattern of a generator matrix is the subsets of matrices, subsets of n, such that, say, the first row, A1 are the entries which have zeros, A2 for the second row, and so forth. There are constraints on what these sets can be. For instance, we can't have them all be zeros, or else it's not an MDS code, or even a basis. So there's these generic zero pattern inequalities that say the intersection sizes of some of the sets have to be at most sum bound. These are, you can consider them to be Hall type conditions. Now, let's say that a code satisfies GZP of M if it always has a generator which attains any order M zero pattern. So here by order M, we mean that although there are k total sets, there are only m possible distinct sets, like in the picture on the right. More formally, if you have some generator of the matrix, that for any zero pattern of order m, there exists an invertible matrix which takes your code, your generator matrix, and turns it into one with the prescribed zero pattern. It turns out that GZP of 1 and GZP of 2 are equivalent to MDS, but beyond that, it is not equal to MDS. So now let's go into the main result of this paper. So we just mentioned each of these applications, list decodable codes, maximally recoverable tensor codes, and trying to find MDS codes of certain generator matrices. And it turns out all of these are the same. They're all equivalent to being what is known as a higher order MDS code. In particular, our main result is that the following are equivalent for any linear code. One is that you're what is known as higher order MDS. Another is that you're this attained generic zero patterns of order M. Another is that your dual is LD-MDS at most m-1, that is, you're optimally list decodable for all lists of size at most m-1. Or, when you tensor with a parity check code, you're maximally recoverable. So, in particular, all of these different concepts are actually more or less the same thing. Now let's discuss the main application of our theorem, which is for Reed-Solomon codes. Reed-Solomon codes are an interesting construction of MDS codes that work for any field of size at least n. In particular, you pick distinct generators alpha 1 through alpha n in our finite field, and then you define a generator matrix, which is the first row is all ones, the second row is the generators, the third row is each of the generators to the second power, and so forth, all the way to k-1. And it turns out every k by k subdeterminant is what you would call a Vandermonde matrix or a Vandermonde determinant, which equals the product of the differences of the elements. And since they're all distinct, this is non-zero. This is related to the fact that a degree d polynomial has at most d roots. A long-standing open question in the field is to understand the list decodability of Reed-Solomon codes. As a baseline, it's known for a random code that for a radius of 1 minus r minus epsilon, you can achieve a list size of 1 minus r minus epsilon divided by epsilon. Further, for Reed-Solomon codes, it's been known due to the Johnson bound, in particular the algorithm Guruswamy-Sudan, that for a radius of 1 minus square root of the rate, one can decode with a list size that's polynomial in the field size and the number of generators. Conversely, it's known for specific Reed-Solomon codes that they are not decodable beyond a radius of 1 minus square root of r if the field size is itself equal to the number of generators. Thus, if one seeks to beat the Johnson bound, one needs to be careful in the choice of alpha 1 for alpha n. In particular, we seek to understand when alpha 1 for alpha n are chosen uniformly at random from this field for a large enough field size. So in particular, there's been much work on understanding the list decodability of random Reed-Solomon codes. In particular, many results have shown that in various regimes, you can beat the Johnson bound. This was started with the work of Rudra Wooters, and many other results have since followed. Our result supersedes many of the previous results and shows that you can in fact achieve list decoding capacity. And in fact, the list decoding guarantees of random Reed-Solomon codes are just as good as random codes for list decoding. Our result also fulfills a conjecture of Shengguan Tamo, who showed that you could achieve this generalized singleton bound for list sizes of 2 and 3, and conjectured you could do it past that. Now let's discuss a bit more about generic Reed-Solomon codes. So by generic, you can think of this algebraically that alpha 1 for alpha n are algebraically independent in some way, or you can think of it as just choosing random values from a very large field. A very important theorem about generic Reed-Solomon codes, known as the GMMDS theorem, showed that a generic Reed-Solomon code achieves its generic zero pattern property for all orders m. So in particular, any zero pattern you want that satisfies the previous Hall inequalities can be achieved for some generically chosen Reed-Solomon code. And from the main theorem that we proved, having this generic zero pattern property is equivalent to having its dual attain the singleton bound for list sizes at most L. And because the dual of a generic Reed-Solomon code is also a generic Reed-Solomon code, we proved that generic Reed-Solomon codes are optimally list decodable. In addition to the results about Reed-Solomon codes, we also showed that for Gabadillan codes, where the exponents of 0 to k minus 1 are replaced with q to the 0 all the way to q to the k minus 1, achieves list decoding capacity in the Hamming metric. Let's now discuss further what we mean by a higher order MDS code. Suppose that our generator matrix has columns v1 through vn, and we call our generator matrix V. So now we're focusing on the columns of the code instead of the rows. For any subset of the columns, we're going to define V sub A to be the span of those particular columns. We also have a generic matrix W, which we can think of as a symbolic matrix with distinct variables or randomly chosen values. Now we can say that our code is maximum distance separable if and only if any k columns of V are linearly independent, or the dimension of each of these V sub A's is equal to the dimension of W sub A. So if you have be a generic matrix, you have some particular value, it should always be W sub A, and V matches that. So in particular, you can then think of an MDS code as some sort of an approximation of generic codes, in the sense that these dimensions all match. We can now further generalize what we mean by MDS codes are similar to generic codes. So as we just mentioned, a code is MDS if and only if the dimension of each of these V sub a's is equal to the corresponding generic dimension of W sub a. However, we can also take the intersection of two of these spaces. So if we intersect V sub a with V sub b for some sets a and b, we can also have that be equal to the dimension of W sub a intersect W sub b. Now, b implies a is easy to prove, as you can just set a equal to b. The other direction is a little more tricky, so let's talk through it. Here, we can use what's known as the inclusion-exclusion principle to write the dimension of this intersection as the dimensions of each of the two spaces minus the dimension of the sum. Further, because of our notation, the dimension of the sum is equal to the dimension of A union B. Now, because of assumption A, we can replace each of these V's now with W's and then reverse our steps, showing that the dimension of VA intersect VB is equal to the dimension of WA intersect WB. Now, you might be asking, can we keep going? So let's now try to take the intersection of three sets. Are these equal? The proof seems to almost write itself, as if I take these intersections as spaces and then just use inclusion-exclusion, again I'm just going to get a sums and differences of some sums. These sums become unions, and then we can swap it out. However, this proof idea is completely wrong. And in fact, this is the number one misbelief in math according to Math Overflow. That is, there is no inclusion-exclusion formula for three sets. In particular, you cannot express the dimension of the intersection of three spaces just in terms of the dimensions of all the constituent spaces. Therefore, saying that MDS codes is approximately generic codes fundamentally breaks down for three subspaces. This leads to our definition of higher order MDS codes. We define an order M MDS code as a code with the property that for any sets A1 through AM, we have that the dimensions of VA1 through VAM all intersected is equal to the dimensions of WA1 intersected all the way with WA sub M. This definition first appeared in a prior work of ours. Note that order M MDS codes are in some sense an order M generalization of generic codes. Further, one can show that MDS1 and MDS2 are equivalent to just MDS, and thus MDS3 is the first non-trivial higher order MDS code. Let's now visualize what we mean by MDS3 being non-trivial. So again, we're now going to be in three-dimensional space, and we're going to have our vectors v1 through vn form the generator matrix, and each of these are three-dimensional. However, since what we're talking about doesn't depend on scaling, we can actually think of these vectors as being in the projective plane in 2 dimensions. Now, the notion of MDS is very simple. It just means that no 3 points are collinear. And this is a very common generic assumption in combinatorics. However, MDS3 is a bit more subtle. It's if you take 3 lines through 3 pairs of points, then these should not concur. So in particular, it's an extra property on top of being MDS that's rather subtle. In our investigation, we also compute a formula for these generic intersection dimensions. In particular, for any generic matrix W, we show that the dimension of WA1 intersect WAL is equal to a combinatorial formula that only depends on the sets A1 through AL. In particular, it doesn't even depend on the characteristic of the field in which you're working in. This result is crucially used to prove our main theorem, as we'll demonstrate on the next slide. We also remark that this formula can also be computed in polynomial time. Let's now work through a special case in which we know that the dual code is higher order MDS, and we seek to prove that our code itself is optimally list decodable. Suppose for contradiction that our code does not have optimal list decoding guarantees. In particular, it's not rho comma L average radius list decodable when our radius rho is L over L plus 1 times n minus k over n. In particular, there exists a message y in code word C0 for CL, such that the weight of each code word minus the message is smaller than what it should be, L times n minus k. Now let's let E sub I equal each of these differences, and let AI be the support of each of these differences. Then we have that the sum of the sets AI is at most L times n minus k. Now, important observation is if H is the parity check matrix of the code, then H of E0 all the way to H of EL is equal to HY. And this is because each code word times H is equal to 0. Therefore, HY is in the intersection of these spaces HA0 for HAL. Further, since these code words are distinct, we can then argue that the dimension of the intersection of these spaces HA0 for HAL is bigger than what it would be generically. And this is because we can compute the generic intersection using the generic intersection dimension formula and show that H sub y is one more than anything in the intersection of H that arises from these generic intersections. And this is a contradiction since our dual code is MDS L plus 1. To conclude, our prior work defined a generalization of MDS codes called higher order MDS codes. As this work shows, there's many applications for higher order MDS codes between list decoding, erasure coding, secure data exchange, and so forth. It would be interesting to know if there's even more applications. One open question we have is whether there exist explicit constructions of higher order MDS codes. Finding nice constructions could help in the theory of pseudo-randomness and other such constructions. Another question is to find relaxations of higher order MDS codes which allow for smaller fields. A recent work by myself, Manik Dar, and Sivakanth Gopi shows that even MDS3 codes require exponential field size. So finding suitable relaxations could help a lot both in terms of constructions and practicality. Another important question is, do random Reed-Solomon codes over polynomial size fields achieve list decoding capacity? And in fact, this question was just resolved in the affirmative in recent works of Guo Zhang and Arabia Guruswamy-Lee. We're hopeful that this theory of higher order MDS codes will have even more applications in the future.